Hi class, in this short screencast I'm going to go over the elimination reaction that we are going to perform in the lab. You're going to begin with an alcohol, that's your starting material, and we'll treat it with an acid. You can use phosphoric acid, you may use sulfuric acid as well. So I'm showing you this mechanism with phosphoric acid. As you can perhaps recall, in terms of writing mechanisms, you're going to first show protonation of the OH, and that's going to give you an oxygen now connected to two hydrogens, and since it's making three bonds, it's going to get a positive charge. That makes a pretty unhappy situation for oxygen, and it would want to leave. Again, recall from class we discussed this. Why is it that it's not, you can't just say that OH negative would leave. It would first have to form OH2, and so it's water that leaves. And the reason for that is because if you were to compare the corresponding conjugate acids, in this case, if you add a proton, you end up with water. In this case, when you add a proton, you end up with a hydronium ion. And so the acidity of the hydronium ion is higher than that of water. That makes water a better leaving group as compared to OH negative. All right, so once water leaves, it's going to leave behind a positive charge. And so you have to think about which protons to remove that were present at the beta position, which you can now use to quench that positive charge, because you have more than one. Notice you have three hydrogens in the front and three at the back. These are all methyl groups. And of course there are two that are on the side. Now if you choose the A protons, let's just show that as well. So H2PO4 with a negative charge is going to come in, pick up the proton, electrons move, you get an alkene. That's one product. On the other hand, if the B protons are removed, so H2PO4 with a negative would come in, pick up electrons, and so the other possibility is right over here. Between these two possibilities, the first that I drew is going to be our major product, and you should be able to figure out why. Notice that on the double bond I have three substituents. On the other hand, if I compare that to the second structure that I drew on the double bond, I have one substitution, three substituent. So we don't have as many substituents, and so this becomes my minor product. Now let's talk about do's and don'ts, how we run in the lab. And the reaction, like I said, is a pretty quick reaction. So you're going to begin with 5 milliliters of phosphoric acid and 5 grams of the alcohol. So you'll begin with setting up in a round bottom flask, and I just said 5 grams of the alcohol plus 5 milliliters of phosphoric acid. You can find out the density of phosphoric acid if you have to at a later time in the back of the book in the appendix section. You're going to add a couple boiling chips, just one is fine usually. By the way, in terms of size, if it's only 5 grams and 5 milliliters, which particular RB flask are you going to take? Yes, please take 25 milliliter RB flask. Do not take 100 milliliters. You're never going to be able to collect your product well. So let's begin with a 25 milliliter flask. Let's put our material in there, and we are going to kind of just swirl it, stir it, whatever you want to say. And after that we are going to set up a short path distillation for this reaction mixture. Notice what's going to happen. You basically are beginning with an alcohol So you have an alcohol like I showed you, and it's going to get converted into an alkene, or in this case a mixture of alkenes. And you will have to say major minor, of course, and you will also have to say identify that on the GC, and explain what's where. So you will connect this one to the still head. That should be connected to the thermometer adapter. Again, those of you who did not use the thermometer adapter last class for fractional distillation, please keep an eye on it this time. The thermometer must be placed in such a manner that it is up to the bulb of that should be at the Y junction. You will connect that to the elbow joint, or the receiver adapter, however you want to call that, which has the vacuum port, and the receiver flask. This receiver flask should be immersed in a beaker full of ice. You need to do that because you want to make sure that essentially your product, which is a low boiling liquid, the boiling points are like really low, those are actually, they remain condensed within your round bottom flask. Now I should warn you, the smell of this product, it's pretty bad. It smells similar to feet. So I would like you to please run this experiment in the hood, so we don't all smell like feet, basically. So that's that. And you're going to then carry out the distillation, the short path distillation. So as the reaction occurs, you will see vapors that will rise high, and as they hit the still head, essentially they will leave behind the acid broth. They will hit the still head. The vapors will go up to this part, and as soon as they see a temperature gradient, they would be directed right over here, and they will remain in the round bottom flask. They will liquefy and give you your product. Now so it's a temperature gradient which is pulling the product towards the product flask, and the fact that we are removing the product as it's being formed. So the Le Chatelier principle is saying is applicable here, because we are removing the product from the system. More and more of the a reaction is going to go towards the product, and the reaction goes to completion. So the reaction works really like fantastically well. After you're done, after you have collected and realize it's not that all of the liquid is going to make it on the other side, but you will see a substantial amount. Essentially, the clue to that is that the temperature, even though we say that both of our alkenes, they boil at temperature